Hello, my name is Hubert Shim. I'm on the electrical team specializing in actuators. I'll be providing a general overview of the AUV's mechanical design, as well as the signal flow of our propulsion system.
Hi there, my name is Cameron Fletcher and I'm on the mechanical sub-team specializing in enclosures. I'll be outlining the features and design rationale of our AUV's propulsion system from a mechanical perspective.
Hi, my name is Pavitra Kalra and I'm the project lead for the battery management systems. Today I'll be giving a brief walkthrough of the electrical system associated with the propulsion system, highlight some key design choices, and go over the battery-related safety additions.
Hi, my name is Jake Cronin, and I'm one of the software team leads for UBC Subbots. For the software component of our AUV's propulsion system, I'd like to talk about the control model we've chosen to use, the dynamic model for the AUV, and some of the considerations we made when designing the control system. I'd also like to talk about the implementation of these systems and how we're currently validating the design.
The design of our AUV was to provide a modular platform, allowing us to develop the baseline systems required to compete, and beyond that to provide the ability for future expansion and testing. A variety of mechanical systems come together to make this goal a reality. A frame consisting of aluminum extrusion was selected to allow the AUV to be easily assembled and disassembled. This aids in the logistics of shipping the AUV to competition while providing unparalleled flexibility in being able to accommodate various future subsystems. The frame brings all the other physical subsystems together, providing mounting for the ballast, thrusters, enclosures, and handles. The various enclosures are where all the other components lie, from the battery enclosures providing power, the camera enclosure allowing for sensory input, to the main enclosure housing the computer and control electronics. These are some of the most critical components that make our AUV viable for competition. Finally, the ballast foam and dive weights allow us to accommodate for balancing the buoyant force and center of mass to ensure our design behaves as intended. Altogether, this provides the skeleton on which the rest of the team can grow. The following diagram describes how signals flow throughout the propulsion system. First, various sensor readings are input to the main computer, which enables our robot to make decisions about where and how fast to move. These decisions are then translated into control commands such as speed up, slow down, turn left, etc. In order to translate them to electrical signals, we implemented a software control loop that takes the control commands and maps them into PWM signals, which encode how much power to send to each thruster. Lastly, an electronic speed controller, or ESC, translates the PWM signal into a three-phase input for the thrusters.
The mechanical team's challenge was developing a design for the propulsion system in tandem with the frame and enclosures. The first consideration was creating a base that could be modified to accommodate an undetermined number of components. The idea being that this revision could be used as a testing platform for future components. Secondly, we needed to reduce the cost as much as possible. Our compromise was to design the system to operate with a reduced number of degrees of freedom. The theory behind our thruster layout is as follows. 4 thrusters were placed in plane with the center of mass at 45 degrees to the diagonals. This gave us control over the surge, sway, and yaw, allowing the AUV to have full control over movement in the XY space. Next, vertical thrusters were needed to allow for control of the heave. We decided to place them straddling the main enclosure in plane with the center of mass. This had the added benefit of giving us control over roll. Thrusters were not placed in front of the main enclosure flanges to ensure ease of maintenance of the electronics. Control over roll and pitch were determined to be unimportant, as a higher center of buoyancy relative to the center of mass would generate a righting moment. This was to be tuned to keep the AUV level to the XY plane. Although a mismatch between center of drag and mass would be difficult to control, we determined that this would be negligible at the operational velocities. This leaves our design with effectively 4.5 degrees of freedom controllability.
This section will briefly outline the electrical system associated with the propulsion system. The electrical system ensures that the control commands from the computer get translated to the appropriate power outputs in the thruster. This is a diagram showing the main components of this system. The control commands from the main computer, the Jetson TX2, are sent to a microcontroller which outputs PWM signals. These signals are followed by optocouplers before connecting to the electronic speed controllers, or ESCs. Optocouplers play an important role in isolating noise. Motors and thrusters usually generate a lot of noise which can interfere with more sensitive signals in the system. To tackle this issue, we have two separate batteries for the robot. One battery for the noisy and power-heavy components, and the other for sensitive, low-power components. The optocouplers have an LED phototransistor pair which allows us to make voltage references between the two batteries without actually physically connecting the two. The ESCs then translate the PWM signal to a three-phase motor output to the thruster. Some important design choices we made for this system were choosing the right type of microcontroller and optocouplers. Due to the specific starting sequence required by our ESCs, we needed microcontrollers that could import Arduino libraries and be powerful enough to handle other tasks for the robot. The rise and fall time for the optocouplers played an important role for the same reason. While testing the system, we observed that even when the microcontroller outputs the correct starting sequence for the ESCs won't start properly if the optocouplers added small delays. We also implemented safety systems into our design to protect the robot and the batteries during operation. Both batteries' health and state are monitored by a voltage monitor, current monitor, and temperature monitor. These three values are constantly recorded and the robot operation is adjusted accordingly. If the voltage in any cell gets too low, the robot is shut off. If the temperature or current gets too high, the thruster output is adjusted in order to reduce the load to our system.
For the software component of our AUV's propulsion system, I'd like to talk about the control model we've chosen to use, the dynamic model for the AUV, and some of the other considerations we made when designing the control system. I'd also like to talk about the implementation of these systems and how we're currently validating the design. For the AUV dynamic model, we were able to use calculations done by our mechanical team to obtain all the parameters needed to model the vehicle dynamics. More specifically, the mass, Coriolis, hydrostatic, and hydrodynamic contributions. By linearizing these equations, we were able to develop a model using Simulink to reliably tune our controller, as well as accurately represent the acting forces in our simulation environment to get a better understanding of how the vehicle would behave in a practical setting. We then moved on to make practical assumptions about the model. We assumed that because the vehicle will travel at low speeds, and because all equations are derived with respect to the center of mass, it can be thought of as symmetrical in all axis planes. This assumption allows us to ignore off-diagonal inertia tensor elements, as well as the effects of added mass due to travel. This simplification means that the mass and damping matrices can be thought of as diagonal. We also need to consider that while the mechanical design of our vehicle should avoid any unwanted pitch angle during operation, the thruster configuration does not allow control over this axis, so we wanted to find a way to discourage this motion if possible. And finally, our electrical design prohibits a large overall current draw from the thruster configuration, which we needed to be conscious of. With these considerations in mind, we selected a PD controller with reference term scaling to use alongside a linear quadratic regulator, or LQR, cost function, to use for pole placement. This model allowed us to apply a high cost of actuation on pitch motion and a moderate cost on other inputs to address the current limitations. We also decided to place less emphasis on travel time as the vehicle needed to prioritize stability and low current consumption. To implement our control system and verify its performance, we first created a Simulink project as a workspace to test equations where the inputs were fully controlled and the outputs were easy to view. Once we were confident our model was correct, we moved on to implementing the same equations in C++. With equations implemented in our codebase, we then had to find a way to collect meaningful data without using physical testing or the Simulink model. This led us to develop our own tailored simulation built on the open source simulator Gazebo. When used with our choice of middleware, ROS2, this allowed us to implement all of our detection, decision, and controls logic as if they were being deployed on hardware, and using ROS topics, route all thruster commands to the simulator's custom-built plugins emulating the AUV, and then execute thruster commands and reply with sensor data, all without modifying the code base. Thank you.